Well, hello everyone. My name's Alan Fitzsimmons. I'm a professor of astronomy or astrophysics here at Queen's University Belfast. And I'd like to show you today, or give to you really, a taster of the kind of physics that you would encounter if you come and study with us in the School of Mathematics and Physics. And in fact, I thought, to be fair, what I'll do is concentrate on the different areas of physics that you would encounter just in your first year and just show you how we would take what you learn at A level at school and we expand upon it and push that into different areas. So let's start off with the basics. The basis of all modern physics is actually many hundreds of years old. It was originated by Isaac Newton when he founded the three laws of physics and worked out the equations of motion. Well, we'll start off with those if you come and join us here in the School of Mathematics and Physics, and we'll go over what we mean by force and acceleration and speed and velocity and so on, and see how we can apply those. So, for example, here on the left-hand side, we've got the familiar example of what happens when two balls collide. And what we find in this example is something that's quite fundamental to the subject of physics. We're quite often dealing with laws of conservation, where something we can measure doesn't change. Now, when we deal with an elastic collision, what we find is that both the momentum of the particles and the energy of those particles are conserved. And that's something you may well have met in your studies at school. But we can also deal with aspects of when the collisions are inelastic. That is, that when the bodies deform or one bit moves on to one of the other particles. And in that case, interesting enough, while momentum is conserved, energy isn't in terms of mechanical or motion energy. So that's something we have to take into account in real life physics. And of course, taking these laws of motion and so on, we can start applying them to the world at large, or even the universe at large. And in first year of physics, you'll get your first taste of how we use Newton's laws of gravity to understand the orbits of objects around the Earth and around other bodies. So for here on the right-hand side, we have an image of the International Space Station, which we can see in the evening sky for about a week, once every month here in Northern Ireland. And of course, that is a tremendous laboratory that's used by scientists and engineers, but it's operating under the force of gravity, and therefore understanding how objects work under Newtonian gravity is very important. Now, most of that physics works when we're dealing with low velocities, say a meter per second, 100 kilometers per second, 1,000 kilometers per second sounds quite fast, but it's actually very small when we consider the fastest thing that we know of in our universe, the speed of light, which of course travels at 300,000 kilometers per second. And in your first year of physics, you start investigating what Einstein discovered just over 100 years ago, the theory of special relativity. And one important difference between doing physics at university and physics at school is that at school, you might just be handed the equations and said, okay, we can put numbers into these equations. In university, you'll be deriving special relativity, you'll be deriving Einstein's dynamics from first principles, but also then exploring it and discussing it. So, for example, a famous outcome of special relativity is the fact that time slows down when you move faster and faster and start approaching the speed of light. Well, the consequence that may not have been met before is that actually objects change shape because space also distorts as well as time as you approach the speed of light. Now, another outcome of Einstein's theory, again, which you'll derive in first year physics, is how then the energy of an object depends not only on its momentum, how fast it's traveling, but also its mass. And this, of course, leads to the famous equation E equals mc squared, which, of course, isn't the complete equation. You derive the complete full equation in our physics courses. And we use that equation on Earth to investigate the smallest particles of matter that we know of and even discover new ones. On the right-hand side, we have a picture of the Large Hadron Collider, the largest machine we've ever made on Earth, 28 kilometers across, which we use to probe the very fundamental constituents of our universe by taking energy and converting it into new particles that which we can then study. So all of this comes from special relativity, but all of this deals with motion that's kind of in a straight line. You are going from one place to another, although at different speeds. Another kind of motion, again, something you should have met at school, are oscillations and waves. Now, oscillations, of course, you'll be familiar with in terms of a mass moving on a spring, undergoing what we call simple harmonic motion. And that's something we'll go over in first year physics with you. But also we can then start adding things into these equations, because we know in real life objects have friction. So we can put in friction there and try to figure out what happens to that oscillation as a thing goes up and down on a spring. And then we can say, well, okay, if friction is probably going to slow this thing down, so we can add a force and push it up. Keep pushing it up and back down and keep that oscillation going. And we encounter something called resonance. Resonance is a feature that we see throughout physics whenever there's an oscillatory force. And that might be an oscillatory force due to electric forces or magnetic forces or gravitational forces. On the right-hand side, I've got a picture of just part of the rings of Saturn taken by the Cassini spacecraft several years ago. And what we can see there is a little moon orbiting within a gap within the rings of Saturn. And you can see that wave nature either side, that oscillatory wave nature, either side of the moon in Saturn's rings. And the way we can mathematically describe this and understand this is by looking at the gravitational forces of that moon on the rings around it and finding out that, yes, it turns out we can solve it in terms of looking at oscillations in those rings. So this is one of the beauties about physics. We take a result from one part of physics, and then we can apply that result, that understanding we have, to another part of physics, and we find out that indeed physics and those laws of nature and the way things work in our universe can be understood across a whole range of different subjects. Now, another way to use our understanding of waves and oscillations is to look at light and optics. And one way we do this is by Huygens' principle, where we assume that light travels as a wave. And if we do that, then we can understand that if we have a source of light near the focus of a parabolic mirror, for example, we can solve for how those waves travel and show that coming out of that parabolic mirror, we'd have a plane wavefront. We can actually generate a beam of light, and of course that's what we have with torches and searchlights, any other thing like that. But again, assuming that light is a wave, then we can start investigating its properties, the wavelengths of those waves and so on. And one of the ways we can do that is by the famous double slit experiment on the right-hand side, where we take two sources of light and let those light waves interfere with each other. And that's something that myself and my colleague Andrew will be discussing in another taster video. But one thing that we get out of that is a so-called interference pattern. Now, those interference patterns are very powerful because they allow us to measure the wavelengths of light itself, but they also have tremendous applications. For example, if you ever use a Blu-ray player in a computer console or to watch a film, what you're using there is a laser beam, and that laser beam interacting with its wave nature on the microstructures on that Blu-ray. Well, taking that wave nature of light and going one step further, we now start entering the realm and introducing you to quantum theory, how physics works on the very smallest scales. And we're used to thinking of bits of matter on the smallest scales as little balls. You know, you think of a little ball of an electron going around a little ball of a proton, and that's a hydrogen atom. But quantum theory tells us we can actually think of those particles not as kind of solid spheres, but as combinations of waves. And so on the left-hand side, we can see how in quantum physics we'd represent a particle as a group of waves, or something called a wave packet. And as that wave packet travels and even hits a wall, you can see the waves rebound, and the nature, the structure of that wave packet, and therefore the structure of the particle, has changed. Now, all of this sounds quite peculiar, but we can actually see quantum physics, it happened in real life in our physics department. In our teaching center, in the student area, we have a particle detector called a cloud chamber. And if you watch this video on the right-hand side, you can see streaks occurring in this cloud chamber where particles are generated, radioactive decays are happening. And some of those radioactive decays, forming what we call alpha particle radiation, is caused by another amazing feature of quantum theory, so-called quantum tunneling, where a particle that was once trapped inside the nucleus of an atom suddenly appears outside that nucleus and is free to travel. That is an amazing prediction of quantum theory, but it's something we can see happening 24 hours a day in our physics department and our teaching center here at Queen's. And to be honest, there's nothing better than having a cup of coffee or a can of Coke in the foyer there, and just watching these particles spontaneously appear as they're ejected from the nuclei of atoms. Well, when we look at atoms, we know that one of the forces holding atoms together is the electromagnetic force. And electromagnetism comes from electricity and magnetism. These are two sides of one of the four fundamental forces in nature, one of the four we've discovered in our universe. You'll have met some of these forces already, of course, or you've already started exploring them at school. We're going to explore them much more deeply with you over your first 2 years of your physics degree. So you'll be familiar with electric fields around particles, for example, and the lines of electric force. And on the left-hand side, we've got an image of a diagram of a positive charge and a negative charge, and how we might join those particles and draw the lines of electric force between them. But we can also then look at we can perform experiments. So on the right-hand side, we've got a simulation of the Earth's magnetic field interacting with the stream of charged particles coming out from the sun, the solar wind. And you can see how these charged particles are interacting between those two spheres, and indeed exciting the atoms in that experiment, making them glow purple. And that glow actually is not from atoms, it's from nitrogen molecules in the air, and it's glowing purple because of quantum physics. That color comes from the other physics that you'll be learning about throughout your degree with us. In first year, you'll also be exploring thermodynamics. Now, you might know or think of thermodynamics as understanding the nature of gases, for example. Boyle's law is something that you'll explore in GCSE physics and A-level physics. Well, in in degree level physics, we investigate thermodynamics more closely. And so, for example, you'll see how it is directly related to the motion of atoms and molecules in a gas or a liquid and how that's linked into temperature. But thermodynamics is more about, at its fundamental level, the flow and exchange of energy from one place to another. And now on the right-hand side, I've got a picture of these wonderful wind turbines we now see everywhere to help us move away from a carbon-based economy and avoid some of the more dramatic consequences of global warming. But physics tells us, and thermodynamics tells us, that there's a limit to how efficient you can be. It doesn't matter how good an engineer you are, there's a limit to how much energy you can get out of winds or tides or geothermal heat gradients. And that limit is actually baked into the fabric of our universe. It's not us not being clever enough in terms of building things, because we have amazing engineers now, both in Queens and around the world. But physics tells us there's a fundamental limit to how much energy we can extract from natural resources or any other source of energy. And understanding and calculating what that limit is and how we can approach it is where physics comes in. When we look at the kinetic theory of gases, where we understand temperature and so on, of course, we can go from a gas and a liquid to a third state of matter, the solids, and understanding how atoms and molecules come together in solids is incredibly important. It's important not only for understanding the world around us, but it's important for understanding how we might apply our physics to create new materials and new structures in the future. So solid state physics is the physics of putting atoms together and understanding the forces and the energies that occur when you do that. So on the left-hand side, we've got theoretical calculations of the energy you'd have between two atoms of various different elements when you bring them together. And you'll find out how to calculate those energies and actually how to calculate what's the stable separation of atoms when you try to join them. And again, all of this is based on experimental science, because on the right-hand side, we have a real picture of actual atoms on the surface measured here at Queen's University. We now have the ability to not only image individual atoms, but actually move them around very carefully. And so we can now not only perform these theoretical calculations, but we can match them with our experiment at the atomic level. And that really is a tremendous ability in the modern world. And if you've got a smartphone, and most of you will have, all of that electronics and the capacitive surface for the touchscreen and so on is all based around those solid state physics calculations and experiments. Now, I've talked about calculations a lot. One thing we'll be doing with you in first year, and also a little bit in second year, but mostly in first year, is expanding your mathematical knowledge. Again, we'll be taking what you've done at school and then reminding you, of course, what you've done as well, because you'd have a summer holiday. You know, you forget a few things over then, but we'll take what you did learn, remind you about that, and expand it outwards, because you'll need further mathematical tools and mathematical knowledge to truly explore what's happening on everything from the microscopic particle scale all the way up to the astrophysical scale. So, for example, we'll be exploring with you how we represent three-dimensional fields, and you'll be familiar with that, for example, for temperature, because temperature is a field. Different bits of space around you are at different temperatures, and we can measure that. If we have something like the electric field around a charged particle, then that field not only has value, but it also has direction. And we can work out what not only that direction is, but how that field actually imparts things like rotation and motion on objects. And so you'll be learning the mathematics of that, so that you can understand the physics of what we understand. Now, the other thing about physics, it may be a mathematically based subject. Mathematics is the language of physics, but it might surprise you to know that for the vast majority of real life applications, we can't solve the equations still. They're too difficult. So for when we can't solve equations, we turn to computers and we put those equations of physics into the computers, into computer programs, and let the computer solve that for ourselves. And so computer modeling is quite an important part of physics these days. And we need to therefore to introduce that to you. So for example, in this simulation, we've got two fluids here. One, red, is lighter, less dense, and it's lying on top of a more dense blue fluid. And if we start moving them against one another, we can see what's going to happen in our computer simulation by just including the equations of fluid flow and how fluids act. And we can see that the computer allows us to predict that turbulence that occurs in such an interaction, something that's incredibly difficult to do mathematically and would take pages of mathematics to do. But with computers, we can simulate that just from the basic equations of physics that you learn in the lectures and the tutorials and the assignment classes and so on with us. And so what we'll do with you in first year is that we'll introduce you to computer programming. We won't take you all the way. You're not doing a computer science degree, but we'll give you again the basic tools so that if you want to go off in that direction and you want to explore physics using computer code, we'll teach you how to use computer code from your first year. And most of our students really get a kick out of that. It is also, by the way, very good to have in your CV. It's an extra skill that you would have when you're trying to find a job or looking for a career when you finish your degree. The ability to computer code is actually pretty impressive to a lot of employers. Now, I mentioned that this is something that we can use for simulating our equations, but it's computer programming at a sort of simpler level is something we would also use to actually figure out what we've measured in the first place. Physics is an experimentally based subject. You can come up with the most beautiful theory of how things work in our universe, but if it doesn't match what we actually see, then it's wrong. And that's the scientific principle. If you've got a theory, then the theory has to match what you see. So we'll give you a course in first year on scientific skills. How do we know when a piece of physics is right? How do we measure things? So you'll be in our first year laboratories and making measurements and learning how to handle uncertainties, for example. And that is those skills are the basis of the skill sets that all physicists need. So on the right hand side, for example, we've got a result from a space satellite called Planck, measuring the variations in radiation left over from the Big Bang that's come to us from about 300,000 years after the creation of our own universe. And in this graph, you can see how we've got the data points with their error bars, with their uncertainties, plotted in red, and in green, we've got the theory, the fundamental theory that comes from theoretical physics and equations. And you can see that we can fit that theory to these measurements and actually find out a lot about how our universe started and how it's evolved over the past 13.7 billion years. So getting these skills under your belt is quite important. And in fact, you'll be doing a little bit of experimentation in first year. You'll also do it in second year and of course third year and fourth year, depending on whether you study for the 3-year BSc or the 4-year MSci physics degree with us. So that's all first year physics. There's a lot there, but we've got a whole year to guide you through that, and that's what we'll do. Now, in year 2 and above, the nature of the course will change, and we'll have individual courses just on single aspects that you might have covered before. So, for example, you'll have a whole course just on quantum physics and quantum physics and statistical physics, which can be hard to say. And that will allow you, by the end of that course, to calculate where electrons can exist in the simplest atoms, for example, the hydrogen atom. You'll also get another full module on solid state physics, learning how we can put atoms together and how that affects the physical properties of different solids. There's a course on atomic and nuclear physics where you'll take the quantum physics that you've now got and learn how that builds us up to the periodic table, but also how we can start understanding the structure of the nucleus of an atom. You will take you further into the fundamental force of electromagnetism, and you'll see how we join those forces of electricity and magnetism into a unified force, and how it predicts the existence of light as an electromagnetic wave. And then finally, we'll start introducing you to other topics you haven't met before. So, for example, you'll have a full course on astrophysics. You'll have now, by that stage, got the fundamental physics under your belts, and you'll be able to apply those then to everything else in the universe, and we'll start you on that journey of discovery as well. So hopefully you've enjoyed hearing about what you will do in your first year of physics at Queen's, and how that leads you on to further exploration in year 2 and above. Now, if you've got any questions about any of this, you can always contact us. And so please email us on mp@qb.ac.uk. We've got a lot of information on the website as well, if you want to take a look at that. But what I really look forward to every year as one of the lecturers in first year physics is meeting everyone and seeing everyone in September. And I will be doing that this year as well. And starting them on that journey of discovery, taking you with all that pretty interesting physics that you've learned at school, and then really pushing it outwards so that by the end of your degree, we've got nothing left to teach you. You will have learned everything we know about how our universe works at the moment. And beyond that is pure science. Thank you very much. Have a good day.